this puts us in the following position. We have a function v of t, which we've determined to be some constant vector minus g sub d t times j, and v of 0 has to be equal to v naught cosine theta I plus v naught sine theta j, where theta is just the angle at which we originally projected the object, and theta and v naught is the speed, how fast it was going. Well, we combine this with this. This is one expression for v0, and I'll note that for v of 0, and I'll note that this is a constant and this is a constant because the original direction theta doesn't change. The direction of the motion does, but theta is the original direction. v naught doesn't change. The speed of the object might change, but its initial speed, its speed at the instant t equals 0, does not change. So this is a constant. Now, if I plug 0 in here, I find that v of 0 is equal to c minus g sub d t j, so that v of 0 is equal to this, times, not t, but times 0, and that's just equal to c, and v of 0 also equals v naught cosine theta I plus v naught sine theta j. So setting this expression equal to v naught equal to this, we find that c is just v naught cosine theta I plus v naught sine theta j, according to our initial condition. And we conclude that our vector function describing the path of this object and its motion in time is v of t equals what? Equals c, which is going to be v naught cosine theta I plus v naught sine theta j minus g sub d times t j. We ask ourselves, what does this path look like? How does the object move along the path? And it's not too difficult to analyze that. So let's just take this function and let's agree to combine the two j terms here. So we have v naught sine theta minus g sub dt multiplied by the j vector, and that is the j vector there. So I'm going to write out the function as it is here. V of t equals v naught cosine theta I plus quantity v naught sine theta, and I left something out. No, v naught sine theta minus g sub d t j. Thought I left something out because I'm thinking ahead to the acceleration function where we have another constant. Not the acceleration, the position function. Anyhow, there's our v of t. Now we want to determine what the path of this object is, so we have to find a function x of t that goes along with this. So x of t, well, v is the derivative of our position function, so our position function is an integral of our velocity function. So we're going to have to integrate this function. When we do, we'll get another integration constant. And what we get is the integral of v naught cosine theta I plus v naught sine theta minus g sub d t j with respect to t. Following the integration conventions, I is just a constant, j is just a constant. Everything but t basically is a constant. The integral of v naught cosine theta I is just v naught t plus a constant. Now, I used C1 and C2 for the constants before. I'm going to use C1 and C2 again. It's a different integration. This is not the same constant it was before. We're into a different problem. I would have used D, except I went and used D for the subscript on G. Anyhow, this integral with respect to t is just, didn't write it correctly. Going to cross that out. Put a domino down to pretend I never did it. Going to take 2 dominoes to fix that one. Let's put this domino here so it's less in the way. Okay, well, this integral is v naught cosine theta, and I left out the cosine theta in my hurry to write the t. So there's our antiderivative with our integration constant. And our antiderivative over here is going to be just v naught sine theta times t plus c2, probably should have tacked that on at the end because I still got to integrate this, minus 1/2 g t squared times j. Now, do we have all that on the screen? I think so. Following what we did before, we're going to write the C1I plus C2J as just a constant vector C. And then we're going to write out our components. Again, let's move things over so we're sure that we've got it. I'm not sure I've got it even now. There it should be. Okay. We've got now a general expression for our position function x of t. Now let's impose the condition that x of 0 equals, we can let x of 0 be anything. Let's let our position function x of 0 be 10I plus 2j. Now x of t is just the function we've written out here. And it's a little long to write out, but not too bad. Okay, there's our function, nicely written out. And we see that x of 0 will then equal c plus 0I, since t is 0. And this part of our j function will be 0, and this part will be 0. So I guess we've got 0j, which just equals c. Now, it's not always going to turn out that our initial value is just equal to our integration constant. It's entirely possible that we get a function which evaluated 0 is not 0. But in this case, that's so. And we conclude then that c for this integration is 10I plus 2j. And the final form of our function is x of t equals, we'll write it like this, v naught cosine theta times t plus 10 multiplied by I plus v naught sine theta t minus 1/2 g t squared plus 2 quantity multiplied by j. So this function satisfies our original constant acceleration with our assumed initial velocity and our assumed initial position.